so welcome back to the afternoon session. We're going to have a talk now with Raja, who's going to talk to us about quantum repeaters.
Thank you. Well, first of all, thank you for being here and for this fabulous workshop, Joe. There's a gaming sign on there. Thanks. No, it's not mine. Okay, so today I'm going to talk to you about quantum repeaters, especially quantum repeaters using NV-centered, which is a particular way of doing qubits or quantum memories or that have a good communication interface. So I will explain all about it. This is a work that I've done in QTech, which is an institute in the Netherlands. It's the work that I did during my master, so it's also to show you that you can do some really interesting stuff during your master. And right now I'm a PhD student in Leipzig under the supervision of Eleni that you saw earlier and Jordanis Kerenidis. So this is the outlook of my talk. I'm going to first introduce what is a quantum repeater and why do we need them. Then I'm going to introduce a mathematical framework that I use to model everything that happens when you use a quantum repeater. So from the sending of a photon to its detection to anything. Then we're going to look at actual quantum repeater protocols, 3 of them, and we're going to compare them between each other and compare them with some benchmark that I will also try to define. And then, so yeah, this work was done during my master, and since then we did some changes and we evolved a bit the model. So at the end there's going to be refinements. Anyway, so let's get to it. So we're in the context of quantum communication, right? So our goal is to have entanglement between 2 people, Alice and Bob. And to create this entanglement, what we usually do is that Alice has a qubit in her hand. She's going to entangle it with a photon and send it to Bob through an optical fiber. Then Bob will take this photon and transfer the entanglement to his qubit. So to say qubit, I will say spin. Alice has a spin and takes a photon, send it through an optical fiber to Bob. And this can be done with, at most, a certain number called capacity, which is the maximal rate at which you can send information from Alice to Bob. And this is a well-known result that if you only use an optical fiber, your photon has some probability of getting lost in the fiber, a probability that directly depends on the distance between Alice and Bob. So in easy words, the longer the fiber, the more probability you have to lose your photon during the transmission. So here you have, in a logarithmic scale, the exponential drop of the probability of getting a photon on both sides. So what can you do if you want to send a photon from Alice to Bob and you have this inherent loss? You use quantum repeaters. So quantum repeaters will be something that we will put in between Alice and Bob that will help you send photons from Alice to Bob with a certain rate. So typically here, for example, I put 2 quantum memories between Alice and Bob. I will first entangle the quantum memory 1 with Alice and quantum memory 2 with Bob. And then I will do a Bell state measurement that Fred has talked just before in the middle and create entanglement between Alice and Bob. This is just a very theoretical example. And a quantum repeater will achieve a certain rate, which is the information that you can send from Alice to Bob. It's a bit per second or bit per number of channel uses number. And we calculated using this formula. So the rate will be the yield, which is basically how many bits you can get from Alice to Bob, times the secret key fraction, which is basically how good those bits are. So for any type of quantum repeater that we will study, this is different type of quantum repeater that we'll study. So this is NV-centered, this is fiber, this is beam splitter, this is detector. I will explain how I model all of this. And each time I will calculate the rate using this formula and ask myself, do I beat capacity? Do I do better than using a simple lossy fiber? So that's how I define a quantum repeater. A protocol and an experimental setup that I will put between Alice and Bob that can do better than simply using a fiber. Okay, right? So let's get to it. Now we'll model everything that happens inside a quantum repeater, inside the experimental setup, and calculate rates. So first, let's start with the emission of a photon. We consider in our model then Alice or Bob will have a photon source that will emit a photon with a certain probability PEM. Then it will be coupled into the fiber with the probability PPS, which can also be used to select a certain type of photon, like for timing and encoding or this kind of encoding. Then the photon will go through the fiber with a certain probability, eta f, that is the transmissivity of the fiber that we saw before. And it will be detected with a certain efficiency pdet. So this is some experimental parameter that they had in QTech. It was state-of-the-art like half a year ago, so it might have gone up now. And I will call eta total the product of all those probabilities. This will define the overall probability of sending a photon, putting in the fiber, that it goes through the fiber, and that it is detected at the end. This is what I will call realistic direct transmission. So it's the same as before. I just send a photon through a fiber, but now I also add the probability of emitting it, detecting it, and making it go in the fiber. And this will be actually my benchmark. If I can do better than that, then I have a good quantum repeater. So that's for the emission of a photon and its detection. Now the other tool that we need is NV centers. So I have a very basic model of NV centers, which is basically 2 qubits, one memory qubit that is a carbon spin inside the NV center that has a long life, which means that it decoheres in like slowly. And I have another qubit, a spin qubit, an electron qubit, that I can use as a photon interface. So I can use this spin to send photons that are coupled with this spin. And I can also make operations between the two spins. So 2 qubits that can be swapped, and 1 qubit that can send photons that are entangled with him. What happens inside this, every time you try to do something, every time you try to measure an electron or measure the carbon spin, which mean measurements, you have errors. Every time I try to flip the qubit or to apply some phase gate on it, I will have some errors. Of course, if a qubit is stored in one of the two, it will decohere with time. So that's another source of error. And when you want to send a photon using the electron, it will also have some error. So how do I model this error? I use this very simple channel, which is called the depolarizing channel, which basically tell you that with some probability lambda 2, my state rho will stay the same. And with 1 minus this probability, I will lose all the information contained in the photon. So this is the totally mixed state, which means I lost everything that I had. So with some probability, I keep my photon, my state, and with some probability, I lose it. So these are the parameters that I use. Every time I do a measurement on the electron, I apply this channel to my state with this FM probability. Every time I apply a 2-qubit gate, so namely a C0 gate, I will apply this depolarizing channel with this probability. And every time I do a bar measurement or a swap gate is where you change the state from the electron spin to the carbon spin and vice versa, I will have those errors. So why those numbers? It's you can ask me later. It's experimentally motivated. Now we're just left with decoherence in the memory, and to model decoherence, we chose to apply the depolarizing channel of before and a dephasing channel, which will change the sign of, flip the face of the state with certain probability. So it's the same as before. Every time my electron or my carbon spin will decohere, I will just apply simultaneously those two channels to my state with some parameters that will depend on the protocol. So I will explain on one specific protocol how I calculate them. And finally, the last error that we have in the NV center is the preparation of the memory photon entangled pair. which I model with, again, the same dephasing channel as here, which means that with a certain probability, my photon will actually be dephased. So now I just have to look at a protocol, take the departing state, look for each thing that I do. If I do a measurement, if it decoheres, if it goes through the fiber, I apply the channel, and I find the state at the end of the protocol. So that's what we will do with some quantum repeater protocols. So the first one that I present is called the single crypt protocol. It's very basic. Some would say that it should be actually considered as a benchmark for a quantum repeater, because that's actually what we use to create entanglement between two people. It goes as follows. So Alice and Bob only have one electron qubit each, and they will both prepare these states. So the up and down arrows are for the electron states, and the 0s and 1 are if you send a photon or not. So Alice prepared these states. With certain probability, she sends a photon. With certain probability, she doesn't. Bob do the same. And they both send the state through those fibers. There's a beam splitter here, which means that with 50% chance, the photon will go through. With 50% chance, he will be reflected. And if you have only one detector that clicked, it means that one of the two sent a photon. But since you have a beam splitter, you don't know which one of the two sent the photon. So they both, at the same time, sent and didn't send the photon, which means that they are entangled. Okay? So if one detector click, they have a pair of entangled qubits. Really simple, right? So now I just have to model everything that happens. I firstly calculate the yield. So I will use the formula that I showed earlier. The rate is the yield times the secret key fraction. So I have every time to calculate the yield and the secret key fraction. To get the yield, I just have to look at the probability of getting one click in the middle. So you have to look at all the probabilities that you can have one click at one of the detectors. For example, if no photon is sent, but you have a dark count at the detector, then you will have one click, but actually you don't have entanglement. A dark count is where a detector click when there is no photon. It happens because of thermal excitation. It happens with a certain probability that depends on how long you open your detector and some experimental data that is given with the detector. So with certain probability, a photon will get lost and the detector will still click. That's P0. With certain probability, you will have two photons that are sent from both sides, but since you have this so-called photon bunching effect, they will both go to one detector. So you will have two photons, but still one click. And that's the states where you actually sent one photon, but you got one click. But in this case, that's exactly the case that you want. So you have entanglement between the two. In this case, you don't have it because of dephasing error. So you get entanglement. You get one click with this probability, which is just the sum of all probability of getting one click. Here you get the yield as a function of only experimental parameter. Then I have to extract the secret key fraction. So for the sake of this talk, the secret key fraction is just a function of the qubit error rate, which is the properties of your final state that is shared between Alice and Bob. So at the beginning, you start with this state. You apply all the error channel that I talked earlier. You find the final state. And from this, by projecting on the correct subspace, you can extract the qubit error rates, which are basically how good your qubits is in each base when you measure it. And you compute the secret key fraction using a certain function. So I will not go into detail on this function. There is a lot of different methods to calculate the secret key fraction, and I choose one that I took from another paper, so even I didn't choose it, right? But what's nice is that EZ, EX, and EY only depends on experimental parameter. So now I have the yield and the secret key fraction as a function of experimental parameter. I can calculate the rate of the protocol as only a function of experimental parameter. So for example, here I can plot any parameter as a function of any other parameter. This is this parameter theta that I put here. It's a tunable parameter. So in the perfect case, imagine you don't have losses, imagine you don't have anything. If you put theta equal pi over 4, you will get the perfectly entangled state here. And you should get a peak here. That's the rate as a function of theta. But now, since you have losses and you have errors in the channel, you have this little shift towards pi over 2 of the theta parameter, which means that I should send a bit more photon. My probability of sending a photon should be a bit higher so that I'm sure to get a rate at the end. So for a fixed distance, you can plot anything. And this is the plot that we want to have. So the rate as a function of the distance, it's very nice. It's very easy once you have the functions. You just have to input all the parameters that you want. And you can see that it scales as this curve. This curve is the same as the realistic direct transmission, but over half of the distance. It just means I cut in half I imagine that Alice and Bob are now halfway closer. It's just to show you that it scales, which is actually quite logical, because here what I have is a photon having to travel only half of the distance between Alice and Bob, instead of having to travel the whole distance between Alice and Bob. So that's why you have this scaling as half of the distance. And you can see that the rate of our protocol actually beats the capacity of the realistic direct transmission for some regime. So you get more key using this scheme than using straight lossy fiber. This is nice. Now I will go on to another repeater protocol, which is very basic. I will put NV center in the middle. I will first entangle the spin of the electron of the quantum repeater with the electron spin of Alice's qubit. I will try to do that many times until it works. So that's the first step. Then once it works, I measure Alice spin, and I swap the two states here. So the states of the electron will now go to the state of the carbon spin. So now the electron is free, and I can use it to send another photon to Bob. So then I will try again many times on Bob's side. But while I do this, the state on the carbon spin is going to decohere with time. So that's why we introduced this parameter, the cutoff, which is a limit of the amount of time you will try on Bob's side before starting again the protocol, because you will consider that decoherence has completely erased your state. So nothing works, like the state in the carbon spin is not good enough now to perform a state measurement and to have a good state at the end. So we introduce this cutoff. First, so I start from the beginning. First, you entangle those two spin qubits. Then you swap the state here. Then you do the same on Bob's side, but not too much, because otherwise the state will decohere in the center. If it works, then you can measure the spin, and you just do a state measurement in the middle, and bam, you get entanglement between Alice and Bob, the two spin. BSM is Bell state measurement. So pretty straightforward. I just have to apply all the channels that I defined earlier. Here I have to send photons, so that's the probability of sending photons that I showed. I have some swap gates, I have some measurements. So every time it happens, I just apply the thing to my state. The only thing that I didn't explain is how decoherence works in the carbon spin. So for the yield, it's a straight formula. I won't go into detail here. And for decoherence, you have to estimate how long it's going to take for how many atoms you're going to have on Bob's side, during which the carbon spin state will decohere. So you will apply this dephasing and depolarizing channel that I showed earlier, which are some decreasing exponential. in the number of attempts on both sides. That's the n here. A and B are the parameter like at which speed the state decohere. And A depends on both. So you have to know now how it works inside the NV center. Actually, when you try to use the electron spin to send photons, it will induce some dephasing error on the carbon spin because they are close to each other, so they are kind of coupled. If you try to use one, it will disturb the other. So that's the A0 and B0. And this is just the time it takes for a photon to go to this distance. So you have the reflective index of the fiber over the speed of the light, and you have the distance between the quantum repeater in the middle and Bob. This is LB, 2 times because the photon has to go and come back to notice that it hasn't arrived. And T-prep is just the time of preparation of the photon. So in the end, decoherence is given as a function of, again, only experimental parameter. All of those parameters, you have them in the experiment. It's just a decreasing exponentials of the state depending on all the parameters to sum up. So now it's nice. You have everything you need to calculate the rate, the yield, and the secret key fraction as a function of experimental parameters. So you can do as before and plot the rate as a function of the distance. And you see that this time, this quantum repeater gives a rate that is actually lower than the direct transmission because now we have too many measurements, too many sending of photons, too many errors happening, such that it cannot ever beat the capacity of the velocity fiber. I just say that you have a drop each time at the end because you have dark counts at the detector, and after a certain distance, you cannot distinguish the dark count from the photon that you want to actually use. So for all protocols, you will have this drop at the end, which means there are too much dark counts now. So now the last protocol, which is just a mixture of the 2 previous protocols. We will do the same protocol as before. So first create entanglement between this spin and this spin, then swap the state to the carbon spin, then do entanglement between this spin and this spin. Except that for doing this entanglement between 2 spins, we will use the single click protocol that I showed, that is the first protocol that I did. So we use those 2 spins, we create this state with a certain parameter theta that is completely tunable. If we get 1 click here, we consider that we managed to have entanglement between those 2 electron spins. Then we swap in the quantum repeater the 2 states, and we use the now free electron spin to again create entanglement, generate entanglement with Bob, with the same limit of the number of attempts, because if you try too many times, the state inside decohere. So exactly the same as before, except that I use the single click protocol in the middle. And best state measurement at the end between the 2 states that are here, so that you have entanglement between Alice and Bob. So now I don't have to explain anything. You have all the errors that are into the channels. I can calculate the yield by just looking at the probability of having 1 click here and 1 click here. I can calculate the secret key fraction by applying all my channels and have the final state. So I can directly plot my rate as a function of experimental parameter. So you see that now the theta function, like the theta parameter, is narrow, so you have a shorter range of theta that will give you entanglement. And you see that it shifted again closer to pi over 2, which means that most of the time you have to send photons. You have this drop at pi over 2 that comes from the fact that in this state, if you put theta equal pi over 2, you don't have any entanglement, so it won't work. But most of the time, you have to maximize this part of the state. And this is the rate of the protocol as a function of the distance. As before, it scales as half realistic direct transmission. Because again, you have 1 photon traveling 1/4 of the distance, 1 other photon traveling another 1/4 of the distance, so only 1/2 of the distance is covered by a photon. And you can see that here you can go to longer distances than the one that you had before. And you still beat capacity in here. So now it's super nice because I have rates as function of experimental parameter, and I can choose to not use actual experimental data, but to say that I have a really high probability of emission and of puff selection. I changed the number because I imagine later we will have better photon interface. So this is what we would get if we put an NV center in the cavity. And that's the rate that we will get. So here you see a huge gap and a huge amount of key rate that you can generate better than using a lossy fiber. Or I can say I have perfect gates and measurements. So the FM and FG at the beginning, I put them to 1. And this is what you get with that. So you can play with the parameter and do anything. It's all in Python. It's very nice. And yeah, you can. So as a summary, you have a realistic toolbox to model a quantum repeater protocol. Any quantum repeater using NV Center, you can just use this toolbox to model it. We did some parameter exploration of some protocols. What happens if you have perfect measurements? What happens if you have no decoherence? What happens if anything? And we see that under some realistic conditions, we actually beat capacity. So we can do better than the lossy fiber. But the main drawback is, of course, the time of the experiments. If you would do an experiment that would prove that you have a better key rate using a quantum repeater protocol than using a fiber, it would take you more than a year. So that's the main drawback of this. So now, as I said at the beginning, this work was done 1 year ago during my master. And now we have studied new protocols. We have this new super cool design. I don't know if you like this better than just the fiber. We also studied this one, which is just a mixture of this and this, which get exactly the result that you would think. We changed some technical stuff inside, so it actually matched more what happens in reality. For example, one error that I didn't talk about is that when you send a photon through a fiber, it will dephase with time. It will turn inside the fiber. We changed the distribution of this dephasing error. And also we changed a bit, but that's only technical details that we changed in order to get a more precise model. And this is now the official final plot with the new parameters. So you see that with the single-click protocol, so this curve, we actually get a big gap between the rates of the secret key rate that you get using this protocol and using only an optical fiber. So this gives actually an experiment that is doable on realistic condition within 12 hours over 10 kilometers. We could prove that we have quantum repeater. I have to say that no quantum repeater to this day has been done experimentally, so this is an interesting thing. So I will conclude now. You can try this with your parameter. Just send me an email. I can send you the Python codes, and you can plug in your parameter if you want. There is also a Mathematica notebook that describes the states at each step of the protocol that I can send you if you're interested. Now, the things that I would like to improve is to add 1 qubit gate error that I just didn't take into account in this analysis. They shouldn't add too much error, but since I tried to be very precise and to look at everything that happened, this is missing. I also only looked at NV centers, which have specific types of errors that could be transferred to another type of quantum memories, like superconducting qubits or this kind of stuff. Right now, I assessed the fact that I have a quantum repeater by looking at the secret key rate and comparing it to the capacity, but that's not the only way to assess the performance of a quantum repeater. So you can try to see if you have other idea of doing that. The article is now published on arXiv, and it should be published this month in PRA. So this is quite cool. I'm quite happy. And you can see that just doing your master, you can do enough work to get an article, which is cool. And we have a doable experiment over 9.2 kilometers with the 12 hours that I said. So this work is to be continued. And with that, I thank you with the usual picture of our group, where you can see Eleni, Damien, Fred, Jawad, that I thank very much, Jawad, for being here and for allowing us to do that. And that's it. Do you guys have any question?
The sources of the dark counts, like you said, thermal excitation, but can you be a bit more specific about that?
Sorry?
I didn't quite understand the sources of the dark counts.
The sources of the dark counts.
Yeah, like why do they happen?
Why do they happen? Thermal excitation inside the fiber. So this is an experimental question. I'm a theoretician. I don't have the exact answer to this.
Okay.
But it just happens, right? And even when you buy detectors, it's written on the box that you have a certain dark current rate.
Okay. Another question. You said there was a time where after you passed that time, you say that decoherence has messed up your experiment.
Not decoherence, but dark counts.
No. You said that you should,
yeah.
when you take into account the time of preparation and the number of time you run your experiment, then after that you say that decoherence has really ruined. You can no longer repeat the experiment.
Yeah.
Does that make sense?
Yeah. Well, if you look at.
I think it was before that. Yeah.
Yeah. So, for example, in this protocol.
Yeah.
First, you entangle those two spins, and then you swap the two states. Yeah. Okay, so you have a state in this spin, and now you're gonna use this one to create entanglement here.
Yeah, but
during this time, the state here will only decohere, right?
Yeah.
So, and then you will have a state of too poor quality to use it to create entanglement between the two, because it had decohere. All the information inside the state has been lost.
Yeah. How do you know how many runs you can do, or how much time you have before it has decohered completely?
So that's why we introduced the cutoff. And then it's just optimization. You plug in with different parameters. You say that you want a certain rate at the end, a certain fidelity of the state at the end, and you look at the optimal cutoff so that decoherence doesn't affect too much your state at the end.
So it's like experimental thing, not as a empirical value, something like that.
No, it will depend on the protocol that you use.
Okay.
And how long it takes to send this job.
Okay, yeah.
An empirical value will give you some of the parameters here.
Yeah.
Then you optimize over the protocol to know where you stop.
Yeah, okay. That's
Thank you.
Hello? We have to pretend that it works?
No, it works. That's only for the game.
Okay. So, it works there? Oh, okay, good. So, why are you're still getting an exponential drop? Why? And is there a way to change that? I mean, it seems that you're displacing your exponential drop, but you always have an exponential drop. Is there a way to...
I mean, we're still sending photons through fibers in all our protocols. So you still have this loss inside all fibers that provoke this exponential drop in all protocols, right? Otherwise, you would have to use free space, which is not the model that I use, or other ways to send photons.
Okay.
Okay. You said something about the rate. I did not understand what it was about.
The rate?
Yes.
The rate is how much information you can send from Alice to Bob per number of channel users.
Okay.
So if I have to try 10 times to get 1 bit of information, the rate would be 1 out of 10.
Okay. And the capacity, what is the definition of it?
Capacity is the maximal rate, theoretical maximal rate at which you can send information using a fiber.
Ah, okay.
Capacity then you should read theory of information, some books about it, and
Okay.
it's really well defined for a lot of different channels, quantum and classical. It's a classical notion in the beginning.
Okay, thank you.
That's one. Good. Which slide? This one? Or is that all about quantum repeater? Which one? Quantum repeater. This one? Okay. I said something about? Sorry? Entanglement? Yeah, well, my final goal is to get entanglement between Alice and Bob. Once they have entanglement, they can create keys. So how do we create entanglement? And that's the whole purpose of quantum repeater, right? So the natural way, the first way to do that is just to send a photon from Alice to Bob. And in this photon, you will put the entanglement, like a hand-wavy way of saying it. You put the entanglement inside the photon, you send it, and then Bob retrieves the entanglement from the photon and put it in